Hey, this is Mr. A, and I'm using this fancy light board to teach a lesson on electric fields. So this is kind of what I want to cover in this video today. We're going to start, I'm going to give you an analogy, and then hopefully we'll work our way down to some example problems, okay? Electric fields, electric fields. In the last video, I tried to explain what an electric field was. And I tried to explain what an electric field was in terms of Faraday's theory. Faraday had this theory about electric fields. He knew that if you had two charges, well, let me ask you this. If we had two charges out here, electric charges, what is going to happen to these two charges? Would they feel a force? And of course, yes, they would. Would it be an attractive force or repulsive force? Well, opposite charges attract, like charges repel. So there would be a force on these two charges to get away from each other. Now, Faraday looked at the situation and he says, well, this charge really isn't being affected by this charge directly, it's being affected by this charge indirectly. What does that mean, indirectly? This charge is responding not specifically to this charge right here. This charge is responding to the field around it. So that if the field around this charge changes, then that charge is going to respond. Well, what's the difference? It's kind of a subtle difference, right? Well, when we're trying to solve problems, it helps us to think about the space around the charge and not necessarily the sources that are causing that space to change. Let me give you another example. And this one I actually demonstrated in the classroom. So I had a balloon suspended from the ceiling, and I had another balloon suspended from the ceiling, and both of those balloons had I rubbed them on my hair, right? So they would have a negative charge each other. So the balloons, although they were hanging from the same spot, they didn't come into contact with each other. They actually spread apart because of the repulsive charges. And then I did a cool thing. I put my hand in the space between the two balloons. And what happened? The balloons actually collapsed because I changed that field space. I changed the space between the fields, between the balloons, demonstrating an electric field. All right? All right. Let me talk about that in another way. Maybe you can get it if I use an analogy. And this is kind of a fun thing to think about. Think about dirty diapers or bacon. So here's a really repulsive smell, and here's an attractive smell. Everybody likes the smell of bacon, right? So are you affected directly by the stinky diaper, or are you affected by the smell of the stinky diaper? Well, of course, you're affected by the smell. I mean, you're using your nose to smell, right? So your nose has a particular sensitivity to certain smells. So if you smell a stinky diaper, you are going to react to it, right? So what's people's reaction to a stinky diaper, right? They back up, right? They, oh, I don't like that. I don't like that. So again, you smell the smell. It's the smell of stinky diapers. The source is the stinky diapers, but you're reacting to the space, the smell, the air that's coming in your nose, right? So it is like the stinky diaper field, right? So there is a field of smell. Okay, maybe I'm pushing this a little bit too far. Maybe I want to push this analogy a little bit farther. So it's not only how dirty the diaper is, but it's also how sensitive your nose is, right? My wife, she has a more sensitive nose than I. She can smell all kinds of things that I don't. I might see a dirty diaper and go, it's a dirty diaper. My wife might smell a dirty diaper, the same dirty diaper, and go, whoa, get that out of here, right? So sensitivity of your nose has something to do with it. So I have a little graph right here. So this is repulsive reaction versus nose sensitivity. So for the same stinky diaper, we have a graph that let's use a different color, of repulsiveness versus nose sensitivity, right? So it's the same stinky diaper, right? So this is the thing that's common. But if my nose is like not very sensitive down here, then my repulsiveness to that smell of that stinky diaper is going to be, that's just a stinky diaper, right? But my wife's sensitivity, she might be really sensitive to that, and she is going to have a horrible reaction to that. So, oh, God, get that out of here, right? But it's the same stinky diaper, right? So you might have a nose that's sensitive right here, but it's all the same thing. The slope of this line is all the same. The repulsiveness to sensitivity slope is the same, regardless of the sensitivity, right? Now, what happens if you have a diaper that, let's see if you can see the blue, right? What happens if you have a diaper that is a little more stinky, right? We can draw it on the same graph, right? So, is this diaper more stinky or less stinky, right? Well, the slope of the repulsiveness to sensitivity curve is steeper, right? So it must be a dirtier diaper, because even I, with my low sensitivity down here, am going to have a more repulsive reaction to that. Okay, this is a really silly analogy, but if you understand that, I think you're going to be able to understand electric force. Let's equate my analogy to some of the vocabulary terms that you should have read about in your book already. So electric field strength, that is analogous to how dirty the diaper is, right? A test charge. Oh my gosh, I'm going to have to do a little explaining about what a test charge is. I'd have to get into this, particular definition about an infinitesimally small charge that's put into a field. No, just think about a test charge as being your nose, right? So your nose may be more sensitive than other people's noses, right? So a test charge, in our analogy, is just really your nose. Now, electrostatic force, that is your, whoa, that is your reaction. This is a force that's, whoa, actually causing you to move. So electrostatic force is your reaction. Okay. Now that I've given you the analogy and I've equated the components of the analogy to what we're really actually supposed to be learning about, let's look at how this applies in Okay, what I've drawn here is the example that we've been talking about. In our thought experiment, we talked about a room where we strapped on a vest that was positively charged, and we walked around on this floor that was positively charged. And the ceiling had a negative charge on it. And how did that feel to us when we were walking around? Well, we were pulled down by gravity, but we were buoyed up by the fact that our vest was positively charged, the floor was positively charged, and the ceiling was negatively charged. So we actually felt lighter when we were walking inside this room. Then I talked to you about a CRT, a cathode ray tube, and how with this type of arrangement we're actually able to steer a beam of electrons as it passed through here. All right. So today we've talked qualitatively a lot about this. Now we want to start to quantify what the electric field is. The electric field is inside between these two plates. It's like in our stinky diaper analogy, there's all these smells in between these two plates, right? So, but in terms of electrostatic force that's going to force the particle, that is going to force our positively charged particle from positive to negative, that's what we're trying to quantify. So there is an electric field, if you will, and we draw it like this. Electric field lines go from positive to negative. Our charged particle is inside this electric field, and it is going to move in this direction. Okay? The force that particle is going to experience, it's a real force. It is matter that is being moved. There's work being done by pushing that particle up. So there is a force involved here. Now, the amount of force that it experiences kind of depends on how much charge is on that particle, right? If this was a teeny tiny particle, then it's going to respond less to these positive charges and negative charges that it's in close proximity to. If it was a larger charge, then there would be more of a repulsive reaction to the plus, just like your nose sensitivity. So the test charge, the value, the size of the test charge, we have to include that when we're trying to calculate the electric field strength. That's the value of that charge. This is our test charge and the force it experiences. So if we're trying to quantify the electric field strength, then we need to measure the force and the charge in order to determine that. And that's an easy thing to do. If this was an electron and we knew the mass of an electron and we knew the distance that it moved, we would know the force. And if we actually know the force on an electron, so we can calculate the electric field force. Let's do an example problem. All right, suppose on a quiz or something, now I've written all over myself and I have no place to see. All right, suppose I've given you a problem on the test and I say calculate the electric field force for a given test charge. And the charge on the test charge was 3 microcoulombs and the force on the charge was 0.12 newtons. Could you do that? Well, I've taught you all how to guess. You write the given information. What is the unknown? We're trying to find the electric field force. Do we have an equation for that? Yes, we have an equation that E is equal to F over Q, right? And then G-U-E-S-S, substitute and solve. So the force is 0.12 newtons divided by the charge, 3 times 10 to the minus 6. Pause the video, get your calculator. I think this is an easy one for you to do as long as you know how to do exponents. Did you get the right answer?
40,000.
Newtons per coulomb. Again, newtons per coulomb because it's force in newtons and charge is measured in coulombs. Okay? This was an easy problem. They get a little bit harder. We'll do some in class.